Good afternoon, this is Schweitzer, looking at our initial notes on liquids. This video will focus mostly on external factors affecting liquids. You should note that the internal factors really don't change between solids and liquids. All of our same intermolecular forces are all in play, and we want to make sure that we understand the whole, let's say, decision tree for intermolecular forces. Either way, we'll circle around that to a little bit here, but we're going to focus on this today. What external factors affect liquids? What things can we control? And the one here, we've already talked about temperature, and the other one is now going to be pressure. We'll introduce pressure here as a viable way of sort of affecting liquids. Does pressure affect solids? Yes. Gases definitely. Liquids, yes, but solids maybe not as much in our everyday life. It does at extreme levels, but we might not notice in our everyday life. So a quick little self-check on temperature. What is average kinetic energy? Well, you should be noting that is temperature. What's molecular velocity? Well, when we do this thing, we go kinetic energy average equals 1/2 the mass times the velocity squared. That's your actual average velocity of the particles. And for a given temperature, larger massive particles have slower velocity. As temperature increases, what is the change in physical properties? Well, we should note that we're going to increase our movement. These molecules are going to start moving more. We have rotational movement and we have translational movement. So that affects the state that the molecule is in, because as it starts moving around, we start getting things where liquids start moving more than gases even more, so as we increase our energy. What's the kinetic molecular theory? Sounds funny looking, or sounds complicated maybe, but kinetic means moving. Moving. Molecule means particle. Idea. How should I use kinetic molecular theory to explain pressure? Okay, well, a couple things about kinetic molecular theory. One is temperature, increases movement. That's a part of this idea. Number two is that pressure, which we'll talk about in a moment here. So pressure is essentially, well, by scientific mathematics, pressure is simply force per area. And in most cases, unless you're a Jedi Knight, when you apply or have electromagnetic or gravitational or nuclear, I already realize most forces are when something collides with something else, actual contact force. So the force is really going to be a collision, with a particle on the inside container of a wall. Container wall. That's really important. And that's how we want to describe this with kinetic molecular theory. Divided by the area. And this is going to get played out more in gases, but we already want to get an idea that when something collides, it produces a pressure on that wall. And then the average pressure is just the accumulation of all these collisions happening constantly. So pressure could be deemed by how fast it goes, it hits it, you get more pressure, or just more collisions would get you more pressure. So magnitude of the pressure and the quantity of the pressure, of the collisions. All those things will be describing what causes pressure. What unit should I be familiar with in using pressure? Well, pressure typically would be, an atmosphere is probably our most common, and another one might be a millimeter of Hg, and 1 atmosphere equals 760 millimeters of Hg. Torricelli kind of developed this, so it's also called a torr, after Torricelli. Alright, what about atmospheric pressure? So this literally is if you're standing on Earth, and above you is a column of air, what's the physical weight, which is the force of gravity pushing down on you? And there are high pressure systems, low pressure systems, so if all of a sudden, and our Earth is pretty constant as far as the level of the atmosphere, the depth of the atmosphere, but sometimes it changes where the particles above us are just heavier. You know, they have more mass to them. Same number, just they're more massive. In fact, water happens to be a little bit lighter, less massive. So that was a pretty bad lighter. Okay, so H2O has a molar mass of 18 grams per mole, whereas pure nitrogen or dry air, N2, is 28 grams per mole. So if you happen to have more nitrogen above you and less water, then you get a higher pressure because it's more physically things on top of you. How was pressure discovered? Well, Torricelli really is the one that figured this out. Maybe I spelled that right. He was sort of given the job of figuring out why they couldn't pump water up to certain heights. They could pump water, but they could only hand crank pump this thing. Alright, to certain heights, and that would be it. Turns out they're really using pressure, atmospheric pressure, to push it. And he came up with a method of understanding how this is working, and that in reality we have essentially atmospheric pressure pushing down and pushing liquids up, and you can only support so much. You know, the idea maybe would be that, okay, if you have Earth and you put a super long straw out of Earth into the ocean, would the pressure of the atmosphere be able to push down and drive up the straw and out into space? And the answer is no. So in this case, water, the atmosphere can really only push water up about 28 feet. 28 to 30-ish feet. And then it's just like a teeter-totter. On one side, you have the atmosphere pushing down, and the other side pushing up. Sometimes I make the analogy, if you were to go through a drive-through McDonald's, and you take a straw, suck up a liquid here, and put your finger on it, and it stays there, right? How many straws could you hook together and have this still work? And the answer technically is if a straw is about a foot, you can do 28 of them. Hook them together and suck them all up, put your finger on top, and technically it would stay there. I've tried a variation of this already, and it's kind of unique. So again, what is suction then? There really is no such thing as suction. There's only difference of pressure. So they aren't sucking up the liquid. The atmospheric pressure is pushing down on the liquid here, and then it's driving it up. Okay. Common thing that we'll sometimes discuss here would be if a person puts a glass jar over their face. And you may have experienced this as a kid, where, so I get a face in here. Okay. Alright. Looks like person attempts to, Alright. Person attempts to suck all the air out of this thing. And all of a sudden you get this massive amount of pressure that's pushing down on it. But eventually, it comes to a static amount, but the pressure becomes pretty immense. And it's just the atmospheric pressure. If you were to go up into an airplane super high up into the atmosphere, eventually like this, eventually it would just, in an airplane it would fall off. As the pressure removes, the pressure would be less. It would just fall off. So atmospheric pressure is something that is playing a role in things involving chemistry, not just weather. Alright, so what is vapor pressure? Alright, so we see this a lot. I mean, you go in your refrigerator and you open up a jar of pickles, one of my favorite things here. Alright, and all of a sudden, you got your pickle there, and you're out there, okay, and as soon as you open this thing, it just takes seconds. As you open this jar up, and there are particles of this gas that were above here, escape, and you get them in your nose. You smell it. Okay, your nose is pretty sensitive. So this is that stuff above it. So what happens here is we have a liquid, and stuff exits the liquid and then re-enters the liquid, and we get this sort of static stalemate, you might call it. Alright, between going from exiting and entering the system. That stalemate, I like the word stalemate, gives a better visual of what it is, but in science we call it equilibrium. And this is one of our types of equilibrium that we tend to sometimes focus on. So, what is vapor pressure? It's that pressure that builds inside of a headspace of liquids there. Okay. It's caused by collisions with the inside container of the wall as particles fly around. Vapor pressure. So, that's what it is. Some things inherently have larger vapor pressures than others. Obviously, the pressure inside of a jar of pickles is there. You smell the gases when they come out. Does the pressure just keep building and building and building and building? No, because then the pickle jar would explode. So we come to a balance where stuff exits, stuff enters. How do internal factors affect vapor pressure? Well, you should realize that as the particles attract to other particles, as intermolecular forces in the liquid phase, okay, increase, then the vapor pressure is going to go down. Now, we can't really change the inherentness of one particle to the other particle. Can't change that. But we can assess it and look and say, okay, would we expect particle substance X to have more or less vapor pressure than substance Y? And of course, at this point, you could make that assessment based on the intermolecular forces present. And of course, we would revisit all of our concepts of intermolecular forces. How do external factors affect vapor pressure? Well, as temperature increases, the vapor pressure increases. Okay? Again, it just shoots off, and we would come to a new balance. At a higher temperature, you come with a new equilibrium or stalemate with more particles in here, and therefore more vapor pressure. So if you warmed a jar of pickles and then took the cover off, the smell should be more intense. Here's an example of some of this. Alright, we have liquid methanol and liquid butanol. Student hypothesis: at 25 degrees Celsius, both substances are liquid. Both substances should have the same vapor pressure. Justify or nullify this statement. The answer would be nullify, and the reason for that would be intermolecular forces. Alright, they are not the same, not equal. Okay. At this point, notice that they have different boiling points. Okay. So the boiling points are really being governed by the intermolecular forces. The boiling points of these things are proportional to the intermolecular forces. So it would appear that the butanol has a greater amount of intermolecular forces than does the methanol, even though this thing has an OH, which is hydrogen bonding. This long chain must be jacking up the London dispersion forces, which allows it to go a little higher. So at this point, I would expect the vapor pressure of this guy to be a little bit lower than that of this one. This one I expect the vapor pressure to be a little higher. Why does it have a higher boiling point? Well, we just talked about that. More London dispersion forces. And it also has this guy too, which is hydrogen bonding. Sample below is poured into a container and sealed, and at time X the temperature is warmed. until time y. After temperature y is constant, sketch the graph. So at time x, you warm it. So maybe we have some particles in here jumping off, and you come to a balance, and it just sort of goes like this. This would be the vapor pressure at this particular temperature. And then you warm it until we get to y, and you start having an increase in the evaporation, and you get an increase here. But you hold it now at a new temperature, and the pressure, of course, new temperature. This vapor pressure is now set at this new temperature. And of course, at that new temperature, we just get a new balance. Vapor pressure is right there. All right, what factors affect vapor pressure as far as boiling is concerned? So when the vapor pressure exceeds atmospheric pressure, then boiling can occur. If you're sitting in a situation where, so there's two ways to boil something. You can raise your temperature to increase your vapor pressure so that your vapor pressure exceeds atmospheric pressure. That's your typical boiling situation. So at 100 degrees Celsius is when water's vapor pressure would exceed the atmospheric pressure. Because the atmospheric pressure is 1 atmosphere, or 760 millimeters of Hg, then the vapor pressure at 100 degrees Celsius must be 1 atmosphere, or 760 millimeters of Hg. Alternately, you could use a vapor chamber or a vacuum chamber, and you could take a liquid and put it in here, and we do this in class, reduce out the pressure and boil it at a lower temperature, or out in space it would boil at a lower temperature. If you have water boiling inside of a vacuum chamber, is the temperature actually larger? No. It's going to boil at a lower temperature. We see this occasionally in cities that are high elevations. They boil water bowls at slightly lower temperatures. Okay. Factors affecting vapor pressure. Okay. So again, we have two just generalized questions here. Trying to recap here. CO2 and H3 are in a container. As the temperature cools, which one condenses first? Great question. So because we're looking at vapor pressure, okay, vapor pressure and boiling, or in this case, just the reverse of that process, which would be to condense, then only thing controlling here is intermolecular forces. And at this point, I would say that NH3, because it contains hydrogen bonding, would be likely something that would be condensing first. This guy only has London dispersion forces. This guy's got London dispersion forces and hydrogen bonding. So it's really an intermolecular forces question. Two samples of water, one boils in Hortonville and the other one boils in Denver. Hortonville, Wisconsin, by the way. There we go. Denver, Colorado. Are they the same temperature? And the answer is no. Due to when the vapor pressure is being raised, it doesn't have to be raised as high. So I raise my temperature to cause my vapor pressure to go up so that it can exceed atmospheric pressure. But if this is lower, then I don't need to raise this as high to get over it. Okay. So temperature and pressure can often be seen in a triple phase diagram. This is tending to be below AP standard as far as you're not going to see something that's on an AP test necessarily, but the concepts are there. We'll use it in our class just because it's great for skill building. If you see something like this, this is a solid, this is a liquid, and this is a, I guess this would be the gas section here, not gas. Triple point, where we have all three phases present. Solid, liquid, and gas. This is the point where the temperature really can't ever be exceeded to keep it a liquid. Temperature is not helping anymore. So we just basically have this little blending here at this point where we're always going to be a gas. It's too hot to make a liquid. Now pressure isn't working anymore. Things you might want to note here, we typically have a pressure which would be considered 1.0. Let's put it right here, for example. We call this normal, by the way. Normal pressure. And at that point you come down here and cut across, and this would be solid to a liquid would be your melting point. Coming to here, you would be a boiling point. If you happen to reduce your pressure, you could skip the liquid phase altogether and just go here to here, and that might be like, let's say, a sublimation. So liquid just wouldn't be existing. This is something you might see on other planets where there is no atmosphere, where there's no liquid. So fine liquid water is kind of unique. Thank you very much.